right, so for testing walkthrough, I just want to introduce the major features of this, kind of the major outlines of the hands-on material that we have put on. We don't have a whole interactive hands-on session planned here. However, if you do have questions about this, we'll be available through the chat for a little while after the day is over to answer your questions. There's also a way to interact with us, and this is probably a better way to get a hold of us through just interacting directly with our GitHub tutorial or GitHub repository, because there you can create an issue. This link at the top is not the current one. There's if you follow through the links that we have and that we've given you in Slack, there's a suffix that's appended to this that's specific to this workshop. What's included in Hello Numerical World are argument parsing, a main function that runs the heat equation, and some utilities. And then the important stuff, there are actually, this code is designed in a way that specifically modularizes the kernels. So there are 3 different time integration strategies, which are kind of the highlight of the computational kernel that we want to run. And those three different kernels are split into very small source files, which are invoked from the main heat equation. That makes them isolated and swappable. There's a refactoring exercise we'll talk about later in order to make sure that they're actually swappable so that we can switch one kernel for another. And the question that I want to talk about is, how can we support testing all these different kernel configurations? That means that we want to make some sort of test where we'll exercise the heat equation, and we'll check whether the time integral of where the solution at a particular point in time is matching what we expect the solution should be. There are different kinds of tests. Of course, code coverage will tell us things like, because a lot of our code is actually in parsing arguments and doing a main, the code coverage will give us a lot of flack about whether or not we've tested every kind of option to exercise the code with. If you look directly at the science cases, we'll want to know, does the science match up with, does the model match up with the science? And so for a heat equation, that's a pretty simple test. We take the exact solution of the heat equation and we take the numerical solution, so illustrated by this current line, and we make some sort of error, function to function error. Then there's multiple different norms that we can use to look at this shaded area. This will give us a number that will tell us whether or not our solution is correct. We can also look at the steady state to see whether or not our heat equation is relaxing to the correct steady state. There are farther areas of tests that we might be interested in, such as integration between codes or compile and testing compiles and run-ins in multiple precisions. But for now, let's just do the simple kinds of tests, which are looking at our steady state solution. If you write these tests into a makefile, then you can create something that's like a make check all, where check all will only succeed once it's run all of its test targets. That's what's in there presently. And if make completes, the commands succeed, because the way make works, if something returns non-zero, then make aborts with an error and the entire make command returns non-zero. However, there's a little bit of redesign we might do to make this testing a little bit better if we got rid of some of these intermediate files that are created, because at present, if you test it and you create an intermediate file, then the next test might conflict with that intermediate file that's created there. So what I want to do is, in this testing walkthrough, is just show you how you could do some steps to replace a make file with a cmakelist.txt so that it's scriptable. Cmakelist.txt is a make file generator. So when you build your project with CMake, CMake will create make files and then run those make files to build it. Some advantages of CMake, even though I guess there are some people who are really in favor of CMake, and there are people who say, well, let me change my compiler command line directly. The advantages of CMake are that you no longer have to deal directly with flags to your compiler and your link steps, but you're able to deal with targets, which are the executables in the libraries that you want to produce, and attributes for those targets, which are libraries that your libraries depend on. libraries that your targets depend on, and include directories and compile features. So CXX standard 11 is a compile feature that you would look up inside of the CMake documentation. This CXX standard 11 then translates into different flags depending on which compiler it's using, which frees you from having to support multiple different compilers. And CMake also provides a ctest command, which replaces your make check all. So we'll be able to contrast these two different methods of testing, kind of dig into the weeds of implementing testing here a little bit. In a make file, you can have an implicit rule for creating object files. And like I said before, the flags and features are compiler and system specific. This is the entire CMake lists file that will build the heat equation. And inside of our tutorial, this is kind of step one of the tutorial, add a CMake list.txt that will build the heat equation code. And here what it's doing is it's doing some required stuff for CMake, and it's giving you an option on whether or not you want to build the tests on by default. Configure file is a nice thing you can do, which will insert build time information into your source code files. So this is turning a template version H into an actual version H, which will be present in the final build. Add executable, and so add executable is defining the one target heat. You have to give it all the list of source files it depends on, and then we can define a feature for it, and we can define the include directories that it uses. In order to convert the tests over from a makefile like syntax, you would start with, so in a makefile, you would say, I want to create a final solution curve that is the steady state by executing the heat equation program and then running a check program to make sure that my final solution curve matches what my ideal final solution curve would be to within some tolerance. Then check returns 1 or 0. If we switch this over to CMake, then we'll be creating a test driver to run the executable, check the result, and clean up the outputs. You can do that with CMake lists rather than building a target, which is the final output, and then manually executing. You can enable testing inside of CMake, and then add a test, which is called heat_help, to run heat with the help, to run the program heat with the help option. We can add another test that's crank_n that's running heat with the crank_n. And we'll also want to execute the comparison of the final output. So as a bonus, let's create a test driver that will, this is kind of like the most in the weeds part of the testing, the testing walkthrough, where, after we've dealt with what the code does and we've dealt with how the CMake build process runs, we have to do this one little thing, which is check whether or not the output file created by running the heat equation is matching our expected answer. So I don't know if I have time to go through how everything works here, but essentially this shell script is going to take the algorithm that I want to run and execute the heat equation. And then it's going to take the final result of running the heat equation and check this final result curve, and then clean up after itself. And it returns on an error. It returns 1 or 0, depending on whether or not the error it found in the final solution is larger or not than the error bound, which we set as 1 10 to the -7 here. Once all of that's converted over, and for more details, since I'm going through this a little bit fast, you can see the example that we put up. Once all of that's completed, then you can compile your process with CMake to build your make files, make and cd test and ctest, and you get a nice testing result. You can go a lot farther than doing simple tests like this. You could think about learning a little bit more by testing, reproducing these testing strategies on another repository. You could brainstorm some simple tests you could add to your own projects. Think about things that you've run manually in the past, or things that are difficult to set up and reproduce cases that you might automate. If you add some blank tests to your project, even if they don't actually test anything in your source code, you've still made a big win, because you've created the infrastructure that's necessary, which now reduces the barriers to adding more tests in the future. And to dream a little bit more, you could ask yourself the question, what would make reporting on the status of your project simpler or more accessible? So what are the kinds of things that you usually do when you test it, and how could you automate those steps? All right, so that's my testing presentation. And it's telling us that there's good strategies for both make and CMake. And I think we've been able to compare kind of the nuts and bolts of what goes into a test when you're actually in the weeds and building these things. Are there questions or comments?